So we have an acute triangle ABC. H is the orthocenter. This one looks tricky. Or look at that orthocenter. It's like really close to A. All right. Omega is the circle through B, C, and H. So I've seen this kind of idea before. That circle, so if you draw the point, I think if you reflect A over BC, it lies on that circle. That's what I would guess. Hold on just a second. Yeah, the reflection of A over BC and the point which makes a parallelogram both should lie on that circle. Whoops. Yeah. And gamma is the circle with diameter AH. It's my midpoint. And then X is the other intersection point. So AE is the median, I'm pretty sure. This is all very familiar. This is just Humpty point stuff, right? Yeah. So, I mean, really, we could pretty much erase this circle, but I'm just going to leave it there for now. X. Okay, so they call this X. And then they try to reflect the whole circle over AX, which is interesting. So I'm reflecting this circle about that line. And then we have another intersection point. Interesting. So that point is Y. And AH, okay, we do need this circle because AH, so Z is really the reflection of A over BC. I could prove that later. We want to show the circle A through AY and Z passes through F. So we want to show AF, YZ is cyclic. Let's see. It's kind of interesting. And we know AFZ is isosceles. So another way to say it is we want to show AYF plus EAF is 180. Is that just an angle chase? Yeah. The reflection of A over F does also lie on that circle. You're right about that. All right. So we want to show AYFZ is cyclic. Let's see. Is there a way to do it? Power of a point? Probably not. But let's see. Let me draw Fy. So what does it mean for y? Yeah, we have to use that we're reflecting one circle over AX. We try to show AYZ equals AMZ. Or yeah, so yeah, I called it F, but yeah, M is probably better. But yeah, how do we get a handle on point Y? So the circle, yeah, what does it mean that we reflect the circle over AX? I'm trying to think how to work with that. Let me reflect the center, see if that does anything. Does D prime, am I missing something, or does D prime really lie on AC? Yeah, no, D prime doesn't necessarily lie on AC. It just looked like that. AHZ or AHX equals XYA. Yeah, that's true. That's a good way to think about it. Since I like that. So XYA is AHX and XYZ So let's see, is XY the angle bisector of AYZ? I think it might be the case. Yeah, I think XY we have to show is the angle bisector of AYZ. I think that's true. Okay, I think we've solved the problem basically, because XYZ is equal to AXHX and AYX is equal to AHX. So yeah, I think I've solved the problem. Yes. All right, so I'm gonna write it up. So I didn't even need a lot of, well, yeah, I needed that Z. Yeah, I'm just trying to think. We'll just write it like this. So let M be the midpoint of BC. Then by properties of Humpy points, AX and M are collinear. We'll just say that. Yeah, I'm just saying, I'll just say by the HM theorem. I think it's video 5 on my channel. I'll just say see previous video.
Hey, Michael.
Hey, John, how's it going?
I'm fine, and you, how are you?
Pretty good. Thanks for joining.
I'm sorry. I'm late. It's because I was having lunch and I didn't come last class because it was actually the day before the Math Olympiad, the Brazilian Math Olympiad. So I wanted to not do anything related to math, and I didn't actually come here.
That's a good strategy. Yeah, you can't be doing math all the time, right? You got to take a break.
Yeah.
But yeah, good to see you. So thanks for joining.
Just for curiosity, on the math test from the juniors Brazilian Math Olympiad, there were 2 problems from geometry, and the problem 5, which was one of the most difficult from the test. I just did the problems from geometry. There were 2, and I just did the geometry problems.
Oh man, so you were just pure geometry. You did all the geometry.
Yeah.
Wow. All right. Well, then my channel definitely.
So yeah, that's it.
You definitely like the theme of my channel then. All right. So what was I gonna do? So M is the midpoint of BC. And then by the HM theorem, A, X, and M are collinear. So I call it the HM theorem. Everyone has their own name for it. Some people just say, most people say Humpty points. So I'm just going to write it like that. So yeah, basically this video on the HM theorem, it says if you draw the perpendicular from the orthocenter to the median, and it's X, then BHXC would be cyclic. So we're kind of using the converse of it here. But either way, AX and M are collinear. And then also, it's well known that the reflection of H over BC lies on the circumcircle ABC. And so that means that if you reflect the circumcircle of ABC over BC, it would have to pass through H. So I'll just write that out. So the reflection of H over BC lies on the circle ABC. And so then by symmetry, the reflection of ABC over BC passes through H. Does that make sense to everyone? So if we reflect that whole circle over BC, it has to pass through H by symmetry. So that means BHCZ is cyclic. All right. And not only that, AE is equal to EZ from that same fact. Because if we take the whole circumcircle of ABC and we reflect it over BC, we get this circle through BZC and H. And so yeah, AE has to equal EZ. Okay. So that's starting out. And then so angle XYA has to equal angle XHA. So just thinking how to write this. So I'll just write it like this. The reflection, yeah, what if I just do this? I reflect y across ax. So there's a lot of reflecting in this problem. I kind of like it. So the reflection y prime of y over ax lies on, what's the circle with diameter ah? Capital gamma. So then we have angle AYX is equal to angle AY prime X, which is equal to angle AHX. We also have angle XYZ is equal to angle AHX. And so that means that angle AYZ is 2 angle AHX. And that's 2 angle AME, which is angle AMZ. And so since AYZ equals AMZ, AYMZ is cyclic. So that solves the problem. So I'll just state it the way the problem says it. The circle through A, Y, and Z passes through M. Yeah, thanks for the idea in this here, John. I think that was really the key, was realizing that angle AYX is equal to angle AHX. All right, so I will move on to the next one. Let's see, these have all been 2020 so far, I think. Yeah. What? The problem is sometimes like a problem disappears, but I have ones from 2018 and 2015, so I guess I'll start on those. Let's see. I think I looked at this one really quick. It looks interesting. So the bisector of angle A intersects BC in point D. And it intersects the circumcircle in point E, which is the midpoint of arc BC. All right. K, L, M, and N are the midpoints. So we have a bunch of midpoints here. AB, BD, CD. It's kind of interesting. So they call it K, L, M, N. So I can see right now, I think KLMN is a parallelogram. So let P be the circumcenter of EKL. This is really random. Okay, so we have two, so KL is equal to MN. And yeah, we have like a parallelogram here, but we want to draw the two circumcenters. So let me do it this way. I hope these aren't like huge. Oh boy, they're like really big circles. Let's draw those two centers. So P is the center of D, and Q is the center of E. We want to show angle PEQ equals angle BAC. All right, let me just check that out. Angle PEQ, 61.5, I think, maybe 64.5. BAC is also 64.5. All right. Let's see. Let me check who's on.
Michael, isn't I didn't prove it, but I drawed it in my GeoGebra, and drawing connecting EQP, it makes a right angle, doesn't it?
Let's see. Angle. I don't think angle QEP.
EQP, Q.
Oh.
I don't know. I don't think so.
Yeah, because by symmetry, I would think if EQP was right, then I would think EPQ would have to be right also by the same argument.
Yeah, I noticed that too.
That's an interesting idea. But PQ has to be perpendicular. So yeah, we know KL is equal to MN. Let's see. So yeah, this is a tricky one. So we could try to get angle QEM and PEL. I wonder if angle LEQ is equal to angle PEM. Oh no, those are like almost collinear if that could be. This is like a weird problem. So BAC is 180 minus BEC. I don't even know where to start here. This is just like a really weird problem. I guess one thing I could try extending. Yeah, what if I like. No, I don't think that does much. Yeah, I really have very few ideas on this so far. Let's see. Maybe I could try drawing it a little differently. Maybe that might. Yeah, it's hard to. Yeah, I just needed like a smaller triangle ABC. Yeah, you have to use the fact that that AE is an angle bisector. So let's see, EB is equal to EC. And then these are all parallel. BL is equal to LB, and DM is equal to MC. So yeah, there's a lot of equal segments here. Maybe it'll even be worth drawing this point.
Is angle LEM equal to angle like BAC?
Maybe. I think I checked that before though, and it wasn't. But I'll check it because like I was testing whether QEL is equal to PEM, and they were different. Well, let's see, 76.4. Yeah, they're different.
Is PEQ similar to ABC?
Is PEQ similar to ABC? Possibly. Let me check. So 76.2. I don't think so. I think they're pretty close. I think Irijon had an idea. Hold on one sec. Let me check. Yeah, Irijon, if you have an idea, yeah, feel free to let us know. I think I saw you raise your hand. Yeah, it almost looks like A lies on one of the circles here. Yeah, it's. How do we figure out angle PEQ? Can we break it up into like PED plus DEQ? I don't know how much that helps. Or it's like it's Q. Let's see, it's QEM plus P. Yeah, I'm not sure. FPEQ might be cyclic. Oh, I missed Urijan's earlier message. So let's see. First, I'm going to check is FPEQ cyclic. Yes, and it also looks like it might pass through L. No, I don't. By symmetry, I don't think it can pass through L. But wait. Oh no, FP. No, it just looks cyclic in that figure. But yeah, it's not cyclic in general. AE, B, and BED. Yeah, AEB and BED are similar. That's an angle chase. So yeah. Whoops, sorry. So yeah, AEB is similar to BED by angle chasing. And L is the midpoint of BD, so maybe that somehow helps. Yeah, it's such a random condition. Angle PEQ. I think. Yeah, maybe there's some congruent triangle somewhere, like because BE is equal to EC. I wonder if BQ is equal to CP. That would be kind of interesting. Take M the midpoint of BC, then MEC is similar to CEA. I don't think so because M is the midpoint of let me see. MNE also kind of looks isosceles. Yeah, I think you might be onto something. MNE does look isosceles, but it's not. But MN is equal to KL. It's half of AD. But yeah, for Urijan, I'll just message him. All right, let me draw this. BE is tangent to KEL possibly. Urijan has an interesting idea. BE is like tangent to this circle and CE tangent to that circle. I think that'll be pretty key if that's true to solving this problem. Yes, it looks very true. So how do we show BE is tangent to this circle? So we want to show angle BEK. I guess we could show BEL is equal to LKE. So yeah, it's probably stuff on medians, I would guess. So let me see if there's an easier way to prove it. So we want to show angle BEK is equal to angle KAE. But KAE hold on a second.
Wait, but A isn't on that circle, is it?
Yeah, you're right. I got confused. A is not on that circle, so we can't say that. I'll try that diagram for a sec. We want to show BEK. I guess we'll have to go with BEL. So we want to show angle BEL is equal to LKE. And LKE is equal to KEA. So we want to show that EL is a median. But EL is the median of DEB. So yeah, I think that proves it. So yeah, so we know I can prove that BE is tangent to this circle and CE is tangent to the other circle, because basically the triangles BEB and BEA are similar, but they're oriented the opposite way. So you can prove that by an angle chase. So BEB is similar to BAE, but they have like an opposite orientation. So since EL is the median of one and EK is the median of the other, then angle BEL is equal to angle KEA, which is equal to angle LKE. And that shows that BE is tangent to that circle and CE is tangent to that circle. All right, so I like that. Maybe that might help.
Sounds like an angle chase from now on, right? Because like PE is perpendicular to BE and CE is perpendicular to QE.
Ah, you're right. So they're both perpendicular. But yeah, I still wonder how they're both perpendicular.
Michael, wait, can you repeat the proof for the tangency?
Yeah.
Please.
So so you can show that triangle BDE is similar to BAE through an angle chase because so yeah, so if you look at triangles BDE and BAE, basically angle EBD is equal to angle EBC, which is equal to angle EAC, which is equal to angle BAD, right? So BDE and BAE are similar. Does that make sense?
Yeah.
And then once you know that, they're similar, but it's kind of like if you look at them, like if you look at point E and you draw the angle bisector of E, it's kind of like if you flip one over the angle bisector, you get the other kind of. You kind of see what I'm saying? You'd have to scale it. Like if you took triangle BED, if you reflected it over the angle bisector of BED, and then you scaled it, then you would get BEA, right?
I think it makes sense, but I didn't actually understand, but that's okay.
Sorry. So actually, here's maybe an easier way to think it. You don't even have to make it that complicated. So, but you understand that BED is similar to BEA, right?
Yeah.
And
Yeah.
L is the midpoint of BD and K is the midpoint of AB. So basically, L and K are corresponding points in those two similar triangles, right?
Makes sense.
So that means that since they correspond to each other, you have to have angle BEL is equal to angle AEK. Because those are like,
Oh, that makes more sense.
yeah. And then KEA has to equal LKE because those are parallel. And so if LKE is equal to BEL, then that shows that BE is tangent.
Nice. That's pretty much easier to understand.
Yeah.
Thank you.
You're welcome. So, but yeah, I wonder, and then like Enrique said, that means so now that we know they're tangent, PE is perpendicular to EB and QE is perpendicular to EC. But I still wonder how to finish it off. So yeah, another way to say it is we want to show angle PEQ plus angle BEC is 180. That would prove it. Is PEQ plus BEC equal to PEB plus QEC? I think PEC equals QEB. Is that true? PEC is 20, QEB is 20. Yes. So it's basically equivalent to proving that. Are those triangles similar? I don't think. Actually, let me check. I'm not 100% sure. So BE and EC. Oh, you're saying that's true because PEC plus 90 is BEC. Ah, that makes a lot of sense. Does that solve the problem? Let's see. I think that might solve it. I'm just trying to think through it all in my head. I think that does solve it. Yes. I'm just trying to think of the best way to. Yeah, no, that just solves it because that's okay. So I'm going to write this up. All right. I'll make some room for the text. Okay, so first we have angle EBB equals angle EBC equals angle EAC equals angle BAE. And so that, whoops, what did I do there? And so that means triangle EBB is similar to triangle EBA because they have two equal angles. And then L corresponds to K in those two similar triangles. Since they are midpoints of corresponding sides. And so, let me check it. Whoa. What? Huh. What is going on here? But do I have to make it serif? What? I'll just leave it like that. And so that means angle BEL is, whoops, BEL is equal to angle AEK is equal to, I didn't even prove, but yeah, so I'll just write this quickly, but KL is parallel to AE, since it is a mid-segment of, whoops. And so that means we have angle BL is equal to angle AEK is equal to angle LKE. And so that means BE is tangent to the circle KLE. Whoops. And then once we know that, so similarly, CE is tangent to NME. Okay, now we have PEC is equal to QEB. So I'm going to prove that. So we have angle BEC is equal to angle PEC plus angle PEB is equal to angle PEC plus 90. And then similarly, angle BC is equal to angle no, this should be angle PEC plus 90. And then similarly, angle BEC is equal to angle QEB plus 90. So that means that angle PEC equals angle QEB. And from there, angle PEQ yeah, how did I finish it off? I thought I had an idea. Maybe I didn't end up finishing it. Let's see, so it's so PEQ is PEC minus QEB. So that's 90 minus QEB, which is 90 minus PEC. Yeah, now I'm not sure I have the solution. I thought I did, but I think I might have tricked myself. Oh, I think I have an idea, actually. So, yeah, BEC is 180 minus A. So PEC is 90 minus A. Okay. So, yeah. Equal BEC is 180 minus A. And so angle PEC equal to 90 minus A. And then from there we can calculate angle BEC. I'll just say, yeah, PEC is QEB. Whoops. And so PEQ is equal to, I think I probably went in a circle here. That does it. Yeah, I'm sure there's some ways to simplify the algebra. Let's see. But that does it. So I will, so we have about 20 minutes left. So I'll spend that 20 minutes on the last problem. And that will be it. All right. Do this. Baltic Way. So this is from 2015. Yeah, the problems previously were easier. Let's see. Meets B, C, and D. M is the midpoint of BC. N is the reflection of reflect. Okay, so this is the M. This is N. Then we draw the circumcircle of AMN. And it intersects AB and P and AC and Q. Okay. So we have kind of a Cheva's theorem here. So wait, that is P. This is Q. We want to show AN, BQ, and CP are concurrent.
Do you know, this is a pretty much, I know a problem from Korea. I don't know how to say it in English. Like, I think it's Korea, but it's a pretty similar problem. And I'll just tell you next, like, when you finish this one, I'll just draw it. You can just draw it.
Sounds good.
It's pretty similar. I think it's the same strategy, actually.
All right. This does look really familiar, though. I agree. Like, so yeah, I feel like Cheva feels like the most obvious idea. Let's see. So we have BP times AB is BN times BM. Yeah, let me write out some algebra here on my paper. We have CQ times CA is CN times BC over 2. Yeah, so I'm getting that BP times BA plus CQ times CA is equal to BC squared over 2. All right. Does anyone have any ideas other than Sheva? To me, Sheva seems like the most intuitive idea, but maybe there's another way.
I think like Seva and power of a point.
Power of a point.
Just no, yeah, to prove the Savas theorem.
Let's see. AN, BQ, and CP. Yeah, this looks so familiar. I feel like I've done either this or something like it before. I just don't remember. So let me try this. So A and M is isosceles, right? So angle APM is equal to angle AQN. So actually APN and AQM, wait, never mind. Yeah, APN, actually, yeah, we have a lot of equal angles here. So BPN is equal to CQM. So they're similar.
Is it like, or is it PN? Yeah, they are not parallel.
Yeah, no, they're not parallel. It's pretty close though. But yeah, we have like, for example, this angle is equal to this angle. So yeah, I wonder how we can use that. Feels like it has to have a way to use it. Are these maybe these are similar. 50. I'd be very surprised, but oops. Yeah, I know, because they're not parallel. Okay.
Why is BPN equals MQC?
Because BPN is equal to AMN.
Yeah.
And AMN is equal to ANM because N is the reflection of M over D.
Makes sense.
Yeah. Let's see. Or maybe we use the radical axis theorem to show that those are concurrent. I feel like BPQC might be cyclic. Let me check that out. Yeah. Because let's see why that is. BPQC we want to show is cyclic. It seems like that's got to be easy. I'm just trying to figure out.
Isn't it because NPC equals BQM?
NPC equals BQM. Is that? Yeah, I'm trying to think why that's the case. NPC equals BQM. I think I have an idea. I think we could prove it probably by power of a point. So we want to show that AP times AB is equal to AQ times AC. And we know BP. Yeah, let me write this out for a sec. I think I have an algebraic way of doing it. Equal to AC. Okay. So I think I have an algebraic way to show using power of a point that BPQC is cyclic. I actually think we have to use that algebra. Let me see quickly if there's like an easier way to think about it. Yeah, I think we might actually be able to use Apollonius's theorem. Hold on just a sec.
Michael, can you try to draw the circumcircle of BPQC?
BPQC, yes.
Yeah, and then the circumcircle of ABQ. Let me just for me to see something.
Yeah.
So the radical axis of those is BQ, isn't it?
Yes, the radical axis of two of those circles is BQ. Yeah.
So we need a third circle that its radical axis with this one is AN.
Interesting. What if we did this? I guess that could be the circle.
Yeah, because AN must pass through the point.
What if we try like that?
I think the
No.
other circle was correct
Yeah.
because AN will pass through the point of contact of these two circles.
I actually forgot what, what I just said. I'm sorry. Was it?
I think it was ACP.
ACP. Yeah.
Yeah, so AN will pass through the point of contact of these other two circles.
All right. So, yeah, but then we have to show AN passes through that point of contact, which I think
must be more difficult.
Yeah. But yeah, so I see an algebraic way. Yeah, let me see if we can avoid the algebra, but if not, I'll just start typing it up. dp_dk. Well, what is k? bp_dk. So k is like, is k the midpoint of arc MN? I think you're saying k is the midpoint of arc MN, right? Yeah, must be. Ah. So yeah, AMN KPQ we know is cyclic from the problem basically, but if we could show that BPDK is cyclic, that would be a good step forward. So I'll call that K. So yeah, it's BPDK has to be cyclic because angle KPB is 90 since AK is a diameter, and angle KDB is 90. So that has to be cyclic. But that is trivial because since AK is a diameter, angle KPB is 90 degrees and angle KDB is 90, right? So that proves what you said, right? It's all right. Once we know that, yeah, AP times AB is AD times AK, which is AN squared. So that shows that that's a nice way, that's a nice geometric way to show that BPQC is cyclic. In fact, you could just use power of a point, right? You don't even need angles because AP times AB is AD times AK, and AQ times AC is AD times AK. Actually, you could just use the radical axis. Yeah. I mean, yeah. So then we know that BPQC is cyclic without having to use a lot of algebra. Interesting. And then now, so what do you do using power of a point? I'm going to start writing this up just because we're almost out of time here. Okay, so write it out in the chat. I'm going to start writing it over here. So write out the details using PowerPoint and Cheva. So let AD meet AMN at K. Then, all right, so then we have by symmetry, angle KDE equals 90. And then angle KPB equals 180 minus angle KBA is equal to 90. And so KDPB is cyclic. So we can draw that. And similarly, KDQC is cyclic. All right. So I will draw that, KDQC. And then by power of a point, you have AP times AB is equal to AD times AK is equal to AQ times AC. So BPQC is cyclic. I already drew in that circle, but oh well. And then you said BN times BM is equal to BP times, okay. So then CN times CM is equal to CQ times CA. All right. And now we can use using Cheva. So now, so basically this means BP, but how do we get PA? I think there's still some algebra. So dividing the two, we'd get BN over CN. Dividing BN over CN is equal to BP over CQ EA over CA. And APQ is similar to ABC. So we have BA over CA is equal to QA over PA. And so then just write out the last step. So we have EN over CN times CQ over QA PA over, or I'll just say AP over PB is equal to 1. So by the converse of Cheva, what? Come on. What did I do wrong here? Ah, there we go. I'm having trouble moving. There we go. So by the converse of Cheva, AN, BQ, and CP are concurrent, and we will stop there. So thanks everyone for participating. It's been 3 hours already and we ended with a lot of people. So thanks everyone for sticking it out all the way through. And I will see you next time. Have a good one.